Welcome to class 26 on topics in power electronics and distributed generation. So, we have been looking at the currents and current components in a single phase inverter, and especially the single phase inverter with a capacitor center tap configuration. And we looked at the started off with a DC specification of the voltage, which is linked to the AC terminal voltage specification with some additional inverter parameters. So, the other things that we need to consider is so the DC voltage rating was considered. So, we have to consider the effect of low frequency harmonics on the voltage rating. In the last class we took a close look at the current rating, and we saw that the current rating has thermal implications, and it has implications on power loss and cooling and the temperature of the capacitor core, which has reliability implications. There are other factors such as hold up time of the capacitor, which can be important in DG application. From the reliability perspective, we looked at a simplified model of the component, the capacitor component, as a bathtub curve, which is a commonly used model for reliability, and we came up with an estimate for end of life. So, if you look at the model that we had for the capacitor, so if we have the manufacturer specified L0 as the life at a test measurement point from the manufacturer, TC0, and if you have data at the actual core temperature of TCA, then the life at the actual temperature is approximately given by L0, and we are considering a doubling of life for a 10-degree reduction in temperature of the core, TCO minus TC actual by 10. You could also have a voltage multiplier effect. So, one factor is the effect of the temperature, which is actually a very significant effect. So, you could also have a voltage multiplier effect. So, if you are operating close to V norm is equal to V rated, then this has a value of 1, and it is greater than 1 for V norm, nominal operation of the capacitor to be less than V rated, and rapidly degrading the capacitor if the actual operation of the capacitor is above its rated voltage. Okay. So, many times you can have a 400 volt electrolytic capacitor for a short duration, for a few seconds you might be able to take it up by a few tens of volts above 400 volt, but if you hold it at that level for a long time, it will actually get damaged in a matter of seconds. But for a short duration you can actually take it above the rated voltage. It is not recommended for continuous operation or design. So, in the last class for our design of the capacitor, one of the design points that we had chosen was we considered a capacitor CDC of 4 parallel 150 microfarad 450 volt capacitor to obtain load life of about 4.6 years and power loss in the capacitor bank of 15 watts. So, essentially what we had done was we calculated the current components, then we looked at what the thermal impedance from core to ambient is, and we looked at the ESR, the values of ESR at different frequencies and calculated the temperature. So, we got 4.6 years and the loss in the capacitor in the ESR because of these various current components totaled in both the top bank plus the bottom bank, each bank consisting of 4 parallel capacitors, to be 15 watts. And so, now we are left with to look at what is the final voltage ripple that happens on this capacitor banks because of the different frequencies. So, one frequency is the 50 hertz which goes through the center tap, and the frequency is the 100 hertz which comes on the DC bus, and then you have the switching frequency effects because you have the output low frequency which is getting chopped by the action of the inverter. So, you have the high frequency effects. So, to look at these individual components, we have our CDC is 4 into microfarad is 600 microfarads. So, if you look at the 50 hertz voltage ripple, your voltage ripple at 50. So, this is we had 4.3 amps flowing per capacitor bank at 50 hertz times root 2 for the peak, and the impedance of the capacitor to be 2 pi 50 into 600 into 10 to the power of minus 6. So, this is about 33 volts. So, we also can observe that this 50 hertz applies plus say for example, if the current is positive, it will charge up the bottom bank and it will discharge the top bank. So, you might have plus 33 volts maybe at one instant, but the top bank will have minus 33. So, the total voltage across the entire bank would be not affected by this 50 hertz, or in another instant bottom might be minus 33 and the top might be the other polarity, but their polarities cancel. But on an individual bank basis, this is an important factor to consider. However, on a total bank basis, it may not be observed. It is not observed. Okay. So, it is not seen on VDC. If you look at the 100 hertz effect, so this is we had 1.8 amps flowing through the capacitor times root 2 to get the peak. So, the impedance is 2 pi into 100 into 600 microfarads. So, it is 6.6 volts per capacitor bank. So, it is because this voltage is actually getting this current is flowing as a differential mode current through the bank. So, you have plus 6.6 on top, plus 6.6 at the bottom. So, it adds up. So, it is seen as a 13.2 volt ripple on VDC. If you look at the switching frequency effects, and the switching frequency we have considered is 10 kilohertz, we have 3.1 amp of ripple. Again, we are approximating it to be a sinusoidal component at a single frequency. So, 3.1 into root 2, and if you look at the capacitive voltage drop, this is 2 pi into 10 to the power of 4 into 600 microfarads. So, you have about 0.1 volt. So, hardly any ripple at the switching frequency. If you look at, so this is because of the capacitive effect. If you look at the ripple because of the ESR in the capacitor with a similar switching frequency current flowing through. So, this is now the ESR of the capacitor was 0.41 ohms at the 10 kilohertz. There are 4 capacitors in parallel. So, you have about 0.4 volt due to the ESR of the capacitor, 0.1 volt because of the actual capacitance. So, at the switching frequency you could almost consider only the ESR effect. The capacitor is starting to behave more like a resistor rather than as a capacitor even at the switching frequency. Okay. So, if you so the ESR effect dominates. So, if you look at what is the maximum voltage, the maximum voltage seen by the individual capacitors and just assuming a worst case scenario, we would have 400 volts nominal for the individual capacitors DC value. You have 33 volts because of your 50 hertz effect. You have about 6.6 volts because of your 100 hertz effect. So, you have about 440 volts on seen as the voltage on your individual capacitor bank. So, you have actually a very tight margin of just 10 volts. So, your control has to be very effective so that you do not have large overshoots etc., when you are actually dynamically controlling the DC bus. Whereas, if you look at the overall total capacitor bank voltage, so this is now twice your 400 volts, which is 800 volts, which was our DC value, plus 13.3, which is twice 16.6. So, about 813 volts is your total voltage seen by the whole top and bottom capacitor bank. So, if you look at the ripple voltage above your nominal voltage, so the ripple voltage is about 2% ripple overall, which might seem reasonable. It is a tight design, but it is actually doable. Okay. So, you might have to be cautious about your control design, so that you do not have large overshoots on the DC bus capacitor. So, you have to precharge it slowly etc. Okay. So, if you look at then the overall design of the DC bus capacitor bank, we saw that the first thing that you decide is the type of capacitor you want to use. So, in a voltage DC bus of a voltage source inverter, a electrolytic capacitor is common. In fact, people have started looking at very high reliability inverters, where you might actually eliminate electrolytic capacitors in the DC bus. You might actually use polypropylene type of capacitors, but its value is quite small, and if you want a large value of capacitance to hold a DC bus constant, you will need a large bank. Okay. So, the capacitor type is important, the voltage rating from both DC and ripple perspective is important. The current ripple has implications on life and efficiency. If we feel that you are tight on these two factors, one might consider, say, considering more capacitors in parallel. However, you also have mechanical considerations which you need to consider. From the cooling perspective also, if you put more capacitors in parallel, you have more surface area for your capacitor bank. So, you effectively help reduce your thermal capacitance as long as you keep your packaging space between capacitors constant, but you also have mechanical constraint of volume and size, etc., which means that you cannot go on increasing the number of devices that you could add in parallel. You end up now taking a lot of space. So, from your packaging constraint, you might have mechanical constraints, you might have sizing requirements which might prevent you from adding more capacitors. You also have factors like if you add more and more capacitors in parallel, in the system you are considering components that are increasing, and we know from our reliability studies that if you put more and more components into a physical system, the chances of failure, especially at connections, terminations, breakage of some problems at the connections can increase. So, putting very large number of components in parallel is also not a realistic solution from the perspective of component reliability. Okay. So, people have looked at what is a reasonable trade-off in terms of the voltage ripple, current ripple perspective, but at the same time not having too many components, overly large number of components. Also from a cost perspective, if you put too many in parallel, your cost might actually go up quite sharply. So, now we will actually look at the one of the analysis that we did for evaluating the current in the capacitor and the life of the capacitor was actually the switching models, what are the waveforms in the capacitor due to the operation of the single phase inverter. So, we will now take a closer look at the switching model of the power converter. Okay. So, if you look at the leg of the power converter, we looked at it earlier. The leg of the power converter is modeled as a single pole double throw switch, and if you look at the overall inverter structure, you have the duty cycle coming into your PWM block, where you are doing a comparison between your duty cycle and a triangular carrier. So, we were considering duty cycles in the range between 0 and 1, and the triangle carrier again going as in a symmetric manner from 0 to 1 and back down to 0. And the output of the comparison is the command to the top switch of your inverter, which is S plus. And we also know that this is a model where we are considering exchange of power between two sources. Essentially, the exchange of power is between your AC and DC side, and the variables that we consider as input to the switching model are the two variables that are essentially varying slowly in such a model, and the one variable which is varying slowly is the DC bus voltage. It does not change rapidly because of the fact that we have a large capacitor typically connected to the DC bus. Another slowly varying quantity is your AC current. Again, the reason why we consider the AC current to be slowly varying is because we have a output filter which is typically a inductive filter, and the inductor prevents sudden changes in currents. So, we consider the AC quantity to be also slowly varying. So, the inputs to this particular inverter model is your DC voltage and your AC current, or your V in and your I out. IAC we have labeled in some of our diagrams, IAC as I out, and the output of the switching model is actually the quantities that are varying quite rapidly, which is your output AC voltage, which is VON. We have labeled it as VON in many of our diagrams. There is output voltage with respect to the neutral, or it can be the output voltage with respect to the negative bus, Also something that can vary the output of the switching model is your DC bus currents, which can be your positive bus current, negative bus current, etc. Okay. If you look at the switching model of such a power converter, the question you could ask is when would such a model be required, when would it be useful to us, and definitely it is going to be useful to us if the item of interest is actually close to the switching frequency, or it may be something even which is higher than the switching frequency because of the rapid transitions that can occur because of the switching action of the inverter. Okay. So, if you look at the items of interest, so your input, the variables are VDC and IAC, which we consider to be smooth and continuous, and your outputs are VO, which can be VON, or IDC, which can be on your positive or negative DC bus, which are discontinuous. So, if you need the switching model, if you are considering, say for example, the switching action of the devices, or the diode operation. For example, if you have dV/dt spikes, dI/dt spikes, you might have stress on the inverter, stress on the components, on the transistors, etc., you definitely need to look at the switching action. You may also be looking at the switching loss, so if you consider it E on, E off, etc., these are switching characteristics related. So, if you are looking at it on a detailed waveform basis, that definitely would need a switching model. You may also need to consider ripple effects, for example, ripple in the filter for filter design. So, you might consider delta I in IAC. We consider IAC to be continuous, but it might have some underlying ripple because of the switching action of the inverter, and you want to decide how big inductor you want to put in the circuit. We also saw that we could calculate ripple IRMS current in CDC. So, factors such as that, such factors can be calculated from the switching model of the inverter. Okay. You might also be interested in, say, the PWM spectrum calculation. So, if you look at the exact expressions for the PWM spectrum of say sine triangle PWM, you get Bessel functions, etc. You have components not just at the switching frequency, but also at the side bands. So, more sophisticated PWM modulation methods, if you want to study it closely, you want to definitely look at the switching functions, the switching model of the inverter. Okay. Another aspect which when you study closely, it becomes an important aspect of all power converter design, is how to handle electromagnetic interference. These interference effects are actually closely tied to the switching effects, the dI/dt, dV/dt in the power converter, and also another part of the aspect of the inverter itself, which is the parasitic components in the circuit. Okay. So, a parasitic component that we recently studied is the ESR of the capacitor. What we wanted to purchase was just a capacitor, but we got a resistor along with the capacitor, which is causing problems. Similarly, when you go to purchase a transistor, you do not just get a switch, you have lead inductances, you have capacitance not just from your collector to emitter of your transistor switch, but you can have capacitance between your silicon chip to your heat sink, and these capacitances can actually carry currents, and those currents can actually lead to significant EMI concerns in your power converter. And these components preliminarily you might assume to be ideal, in the sense that you would assume that those parasitics are not there, but in the actual realization of the power converter, if these effects are ignored, then EMI becomes a problem, which addressing at a later stage becomes an issue. It is always good to look at what parasitic components are there in your circuits. You have stray capacitance between your magnetic windings and your body frame of your inductors, transformers, etc. So, these parasitic components, if it can be included upfront, can actually be included with the switching model of the power converter to see what would be a DI/dt now coming with a inductive parasitic, what would be the induced voltage, or a dV/dt now with a parasitic capacitance, what would be the surge spiky currents that go into such a capacitor. So, these analysis, this type of switching model analysis can give you a feel for what is the worst component in your layout, which gives you the maximum headache from a EMI perspective. Okay. But there are actually drawbacks of the switching model too, and one of the drawback of the switching model is related to the fact that the output of the model is discontinuous. So, whenever you have discontinuous functions, you need more data points to actually describe it, and more data points means you have longer computation time, you need more memory requirement. So, you would always like to actually see where you could get away with something simpler, and the something simpler is the average model. Okay. So, one can look at the average model, and the main benefits of the average model is when we are looking at longer time frames. And one important area where you would look at a longer time frame of the operation of an inverter is when you are actually looking at how to control the inverter. So, whenever you are looking at it from a control design perspective, you might say, I want to look at how does a MPPT act over minutes duration rather than over microseconds duration, where the switching frequency effects occur. So, if you are now wanting to do longer term simulations over multiple fundamental cycles, maybe when you are looking at much longer duration, like cyclic mission lifetimes, days of simulation, where you are looking at temperature effects, which cabinet temperatures can actually take hours to settle. So, you might want to look at then a model which can require lesser number of computations which can actually be solved in a shorter time frame and in a simplified manner, but can capture most of the effects of what the switching model can do. Okay. So, another aspect that can be covered by the average model is ability to understand underlying PWM amplifier For example, you might have a low frequency spectrum of your PWM amplifier. In many advanced PWM modulation methods like space vector, discontinuous modulation, etc., one might consider adding a third harmonic. So, you want to look at the path for the third harmonics in the overall system through the filters, etc. You also have low frequency non-idealities like distortions, deadbands, etc., and you may want to look at the model of your inverter from a low frequency perspective to study these effects in a closer manner. If you look at the time steps that are used for computation, of the inverter. So, if we consider say a switching frequency of 10 kilohertz, you are considering a switching period of 100 microseconds. So, you are talking about your time step to be much lesser than your TSW, your switching period. So, if you are talking about for 10 kilohertz FSW, you are talking about time step TSW of 100 microsecond. You might take a T step of maybe 1 microsecond if you are looking at something on a fine grained basis. You might even take it lower if you are looking at DI DTs, DV DTs during switching action, etc. But you can see that you have a constraint of your computation time to your switching frequency. Whereas, if you now look at on an average basis, you might actually just do one computation per switching period. So, you are talking about benefits, advantages of 100 to 1000 times increased speed in your computation. Okay. So, something which might take hours on a switching model can be done maybe in a few minutes or maybe just a minute in your average model. So, to look at the average model, we will start off with again the switching model of the power converter, and we are familiar with the switching model, which is the single pole double throw switch. So, we consider a switch in parallel with the diode, so if this is transistor QP and QN, and the switching is S plus for, say, if you consider this as leg A, and this is IA, is the current flowing out P and N, and our PWM action is generated by sine triangle comparison. So, we have a triangle going between 0 and 1, and we can consider it with respect to a reference, say some reference R. So, we have VAR, if this is VA. So, in the midpoint topology that we considered on a single phase basis, we had considered the neutral to be the center point, which was the reference. So, we have S plus for our switching function of leg A is 1 if dA is greater than your triangle of your PWM, and 0 otherwise. We also know how to relate the duty cycle back is 1 by TSW integral 0 to TSW S plus A dt, and the switching of the bottom switch is SA minus is 1 minus SA plus. So, we can actually write an expression for VAR. The voltage at A with respect to R is S plus V of P with respect to R plus SA minus Vn with respect to R, and we can make use of SA minus is 1 minus SA plus. So, we get this to be equal to SA plus Vpn, or Vpn is our VDC plus VNR. Okay. So, we have a simplified model for our DC output voltage. So, you have consider this as 1. So, this is the switching function description of our leg A. Okay. And if we then average this particular expression over one switching period, we will put a bar to indicate it is average VAR. So, if you now consider the average of SA plus VDC, we will make an additional assumption that VDC does not change significantly over one switching period. So, you get the average of SA plus VDC, and this is the VDC average plus VNR average, and we know that the SA plus average is our dA, and the VDC is not changing significantly. So, we have VAR is dA VDC plus VNR. So, this is the one is the switching function model, and the 2 represents essentially the average model, and you can actually drop these bars without large change, any significant ambiguity in what type of model you are writing, because you know that the switching function represents a discontinuous function, whereas dA represents something that is smooth function which is continuous. Okay. So, similarly, one can actually write the switching function relation between your DC bus positive current IDCP is SA plus times IA, which is the switching model of the current, and if you then take the average here, taking the average of SA plus IA, we are again going to make the assumption that IA does not change significantly over one switching period. This might be a looser assumption compared to assuming that the DC bus voltage is staying constant. It does have implications. For example, this type of model you may not be able to average when your IA output frequency is getting very close to your switching frequency, but for sufficiently large difference between your fundamental frequency and switching frequency, we could go ahead and take the average, and we have IDC average is equal to dA times IA. Similarly, you could take the model for the negative DC bus current. I DC for the negative bus is SA minus IA, which is 1 minus SA plus. So, you will get 1 minus dA times IA to be your negative DC bus current. Okay. So, if you now draw the model of the average model, you have essentially your positive bus, negative bus, your DC bus, capacitor bank supporting your VDC. You have dA IA coming in from your positive DC bus. You have one minus dA IA with respect to N P. If you look at your output voltage, you have dA times VDC generating your output voltage VA, which is going out through your filter. So, it is your continuous current, which is your I out or IAC. If you look at the voltage dA, it is actually with respect to N, and here what you end up with in this model is that this particular point is also linked to the same reference. So, the bottom part of this model, you have a current source which is going into a short circuit. So, you find that this particular path is redundant. You can actually simplify it, and you can make the model to be something simpler. You have essentially dA IA So, this current is now automatically dA IA, and because this current is IA, this current that is going through the negative DC bus is actually 1 minus dA IA. So, it satisfies the same constraint as your as what is there shown over here, and the inputs to this particular model are essentially your duty cycle, your IA, and your VDC. And typically in control applications, you will have measurement of your DC bus voltage, you have your AC current measurements, your controller is actually outputting your duty cycle, and then you could actually incorporate a model such as this for the one leg of the power converter. So, instead of using the average value, now the value of VA with respect to a reference is now a continuous quantity rather than a discontinuous quantity. And similarly, the currents that are coming in are now continuous quantities rather than discontinuous quantities. Also, the assumption that we have made in this model is that the duty cycle belongs to the range 0, 1. If your duty cycle goes out of the range, you might find that your energy conservation equations may not be satisfied, your amplifier cannot generate more voltage than what is available. So, you need to ensure that you are respecting your duty cycle constraints. You also have other non-idealities that you have ignored in this model. You have ignored non-idealities such as dead time, switch voltage drops, etc., which might effectively reduce the actual voltage that will be obtained at the output of this average model. So you can ask a question now in this average model, can we take this particular inverter to be a amplifier gain. So if you consider this particular amplifier as having a very stiff DC voltage, you can see that the relationship between your duty cycle input and your output voltage VA is essentially just dA VDC. So if we consider VDC to be constant, so essentially you have a gain times your input to be your output. So many times we might further simplify from your output voltage perspective your inverter to be considered an ideal amplifier. Okay. So you can, but if you look at it from the reverse perspective, where you are looking at the currents that are coming into your DC bus, your duty cycle might be a sinusoidal quantity, your input current would be a sinusoidal quantity. So you may not be able to take a simple gain model as the relationship between your currents at the input and output. One current might be 50 hertz, and then your ripple now on your DC bus is now starting to occur at 100 hertz, etc. However, between your duty cycle and your output voltage, you have the same frequency effect, so you could consider it to be just a linear amplifier with simplifying assumptions regarding the DC bus. Another factor to be considered when you are modeling a inverter, especially considering when you are looking at one leg, is in this particular case, if you had, this is for one leg of the power converter, if you have two legs, you could consider two such models in parallel. If you have polyphase, you could consider multiple such legs in parallel. So this particular average model can be generalized. Okay. So another factor to consider when you when you are modeling the converter is the effect of PWM delay. So this is especially important when you are considering the bandwidth of the converter to be close to the switching frequency. In engineering, often when we consider something to be close or far, we consider numbers such as factor of 10. So if your switching frequency is 10 kilohertz and if you are considering control bandwidths below 1 kilohertz, then you might say you could maybe ignore the delay effects. But for designs where you want to actually consider switching frequencies which are much closer to your bandwidth, so you may want to have a bandwidth close to 1 kilohertz, but your switching frequency may be just 2.5 kilohertz. And the reason why you don't want to take your switching frequency high is you know that your switching losses would go up with frequency, so you don't want to take it to be much higher than what is really just required. Okay. Then you will have to maybe now look at what are the delay effects that are there because of the PWM. Also many times in modern power converters, the PWM delay gets added on to the computational delay in your digital controller, and so the overall delay becomes an important factor. Okay. So if you consider the PWM operation, and say duty cycle coming down, if in a digital controller your actual point at which you are updating your duty cycle may be at some regularly sampled points. If you are having an analog type of implementation, you might be able to have the exact intersection of your sine wave and your duty cycle wave and your triangle, people have looked at the difference between regularly sampled and naturally sampled PWM, and the performance is actually quite similar. Okay. There are some pulse position changes because of the sampling, but people have found that you get similar performance in the two methods. Okay. But you can see that in case when your duty cycle is close to 1, update over here will give you a fast response for the operation. Your output voltage goes up to a high value very close to when your actuation, your actual computation is updated, whereas say if you look at the point 3, you are updating over here, and now you have a delay between when your actual switching action is taking place and when the computation is being provided from your controller. And this depends on what is the value of the pulse that you are trying to get, etc., and it is a varying effect, but it is modeled as a equivalent delay model of TSW by 2. Okay. So another way of looking at why or whether one can justify such a model for the delay, one can look at the expression for the average output voltage and the volt second match at the output of the inverter. Okay. So if you look at the average output voltage, say VA with respect to say the neutral in our inverter model is VDC into D minus half. So this was the average model over TSW. So if you look at the volt second on a to n basis, you can describe it as integral with respect to time t S plus VDC by 2 minus 1 minus S plus VDC by 2 d tau, where tau is the time with respect to which you are doing your volt second integration. Okay. So at t is equal to TSW, we have volt second A n divided by TSW. By definition, this is what your average is, VAN average. Okay. So if you look at what this means, if you look at your PWM switching cycle, you might have the output of the inverter going between 0 plus VDC and minus VDC by 2. And you might have an average value, and by definition the average cancels out the positive and negative volt second error. And if you look at then the volt second error that you are building up, again assuming that your error is 0 to start with. So volt second error, you are starting off with 0, you are having some negative volt second error, then your volt second error is going to the other side and coming back. So if this was instant 1 at which you are updating your PWM operation, the point at which your error comes back to 0 is at TSW by 2 and at TSW and subsequent points. So if you look at control action, the time to take for the error to go back to 0 is TSW by 2, and many times the delay between when you give a command and the output to go back to 0 and all the subsequent ripple would be such that the positive and the negative volt seconds balance out. So, one could model the delay effect of the PWM leg to be TSW by 2 from also from a volt second perspective, volt second error perspective. So, this often in a power converter is used along with the model of your output filter. People when they model the inverter for digital control might model the inverter as a 0 order hold. So, if you look at the phase delay of a 0 order hold where the 0 order hold is being updated at a rate of TSW is actually the delay is TSW by 2. So, many times people use a 0 order hold model for the inverter with the subsequent analog filter, etc. In case there is sufficient separation between your switching frequency and your control frequency, then people might be even justified in ignoring such delay effects. Thank you.